Okay, so in this video, we are going to talk about the motion diagrams for free fall. So before we talk about motion diagrams, let's talk about free fall a little bit. So when air resistance acts, acceleration during a fall will be less than g. G is the acceleration due to gravity because air resistance affects motion of the falling objects by slowing it down. So let's assume air resistance is present, and then let's use a ping pong ball and a watermelon to simulate the motion of the two objects when you just drop it from a height of 40 meters above the ground. So you can see in the presence of air resistance, the two objects did not reach the ground at the same time. Because the air resistance depends on the speed of the object and its surface area, so it affects the motion of the falling object by slowing it down. And if you look at the graph, so this is a speed versus time plot, not a velocity versus time plot, but you can get the idea from this graph. You can see the slope is not a constant. So the slope is not a constant. That means the rate of change of velocity is not a constant. So you can see it's decreasing for both objects. Now, if you look at the motion of the two objects again in the absence of air resistance, now you can see, I'm gonna play, the two objects reach the ground at the same time. So in the absence of air resistance, all objects fall with constant acceleration towards the surface of the earth. And if you look at a velocity versus time plot, again this is speed versus time plot, but I think you can get the idea from this graph. So you have a constant value for the slope. So the rate of change of velocity is a constant. We call this rate of change of velocity as the acceleration due to gravity, and it's approximately a constant for objects relatively near the Earth's surface. Okay, so now I think you get the idea about the free fall, and let's look at a ball that is thrown straight up. So for that, here's to take the video in 2 steps. Okay, so as the first example, let's consider a rock that is thrown straight up. Let's neglect air resistance. So first, let's draw a motion diagram for the rock that has been thrown upward from the time just after release until it reaches the peak. Now, first I'm going to define a coordinate system. I'm going to take up as positive, and also I'm going to consider launch position as the reference level. So this is my reference point. Now, the first time you take a picture from a camera, it's here, right? And then you take another picture. Let's assume you take pictures every 0.2 seconds. And then it's here. And it's here. It's here. So what do you think? Is the velocity of the rock, is it positive, negative, or 0? Now let's look at the direction of the initial velocity. So initial velocity is upwards. I'm going to draw a velocity vector, and when it is moving upwards, you can see the spacing between two dots decreases, which means it is slowing down while it's moving up. Okay? So the velocity is positive because it is initially upwards. So until it reached the maximum point, the velocity is positive. And then, how about the acceleration? Is it positive, negative, or zero? So the acceleration is acceleration due to gravity is always downwards, and based on the coordinate system, the acceleration should be negative. Now, is it speeding up, slowing down, or moving at a constant speed? What do you think? So in the motion diagram, you can see the distance the object travels every interval of time is decreasing, and that means object is slowing down while moving up. So it's slowing down while moving up. And also you can see the acceleration and velocity have opposite signs. This is positive and this is negative. So when you have opposite signs for acceleration and velocity, that means the object is slowing down. The acceleration due to gravity causes the ball's velocity to decrease at a constant rate until it reaches maximum altitude. So the velocity of the object decreases by 9.8 meters per second every second until it becomes a zero at this point. So at the turning point, the velocity will become a zero, because in order to turn around, the ball's velocity must pass through a zero. Therefore, at a maximum altitude, so this is the maximum altitude, maximum height or altitude. At the maximum height level, the object's velocity will become a zero. And then let's draw a motion diagram for the same rock from the time it reaches its peak until it falls back to the same height it started. So the first time you take a picture from a camera, it's here. And assume you take a picture every 0.2 seconds until the rock reaches the initial height, and then it's here, and then it's here, and here. So what do you think? The velocity, is it positive, negative, or is it just zero for the rock while it's moving downwards? So you can see the initial velocity is zero. You started at rest at the turning point, and then the velocity is going to increase while it's moving down. The magnitude of the velocity increases by the same amount. Okay. Let's increase a little bit. So the velocity is downwards. Look at the coordinate system. So we defined up as positive. So based on that, velocity is negative. Okay? And the acceleration, is it positive, negative, or zero? The acceleration is downwards, and based on our coordinate system, it will have a negative sign. So it is negative 9.8 meters per second, so acceleration is negative. And is it speeding up, slowing down, or moving at a constant speed? So in the motion diagram, you can see the distance between two dots increases while it's moving downwards. That means it's speeding up. And the velocity and the acceleration both are in the same direction. Velocity is negative, acceleration is also negative. That means both have the same sign, and object should be speeding up. Okay, so then let's compare the motion diagrams for upward and downward motion. Since gravity provides the same acceleration to the ball on the way up as on the way down, the time to reach maximum altitude is the same as the time to reach its launch position. So G is 9.8 meters per second. And when it is moving up, the object is slowing down because the gravity acceleration due to gravity is downwards. And when the object is moving down, the object is speeding up because the velocity and acceleration both are in the same direction. So just a side note, if you look at the height level, at the same height level, the two motion diagrams at the same height level, the object has the same magnitude for its velocity. Okay, and also the magnitude of the initial velocity of the ball is same as the magnitude of the ball at the instant it reaches the point from where it was launched on the way down. Okay, so that's why I have the same magnitude for the velocity vector to represent that they have the same magnitude. Okay.